Yes. Okay, welcome. So, last week we got started on the electromagnetic side of the story. So far only classical, but this week we're going to jump into the quantization of the electromagnetic field and really learn something worthwhile there. So, quick recap. So we had a look at Maxwell's equations. And we managed to rewrite them in a manifestly covariant form. So in terms of this 4 potential A mu, which incorporates the usual scalar potential and the vector potential. So we convinced ourselves that this certainly gives a wave equation that satisfies the relativistic principle. So certainly the relativistic criterion there is satisfied. For the quantum side, it will come this week. But we also noticed that in general, this equation can be a bit unpleasant because it has this gauge symmetry to it. It has 2 redundant degrees of freedom in there because we know that the electromagnetic field only has 2 local degrees of freedom, 2 polarizations. So what we did is we did a gauge fixing to get rid of as much of this gauge redundancy as possible, such that it's much easier to see where the physical degrees of freedom are actually residing. And the equations we then got are simply the D'Alembert acting on the vector potential. So this is really the, if you like, the wave equation. And the other equation that is supposed to be satisfied, which is just saying that scalar potential is 0, and the divergence of the vector potential vanishes, that is exactly the Coulomb condition. So these are the 2 classical equations that the field, the free field, so in the absence of matter, have to satisfy. In this particular gauge, the expressions for the electric and magnetic field, they are also quite simple. Our electric field is just minus the time derivative of the vector potential. And the magnetic field is simply the curl. And we started looking at a general solution of this wave equation in a box with periodic boundary conditions of volume V equal to L cubed. And we recalled from our electromagnetism courses that we know perfectly well what the energy is that is stored in this electromagnetic field. And it's simply given by taking the square norm of the electric field plus the magnetic field square norm and then integrating it over your volume. So in terms of the vector potential, we have to take the square of the time derivative and then the square of the curl of the vector potential. Now that's very nice that we know very well what the energy is. So we're in a very good position as soon as we're going to quantize to actually know what the Hamiltonian will be and what the energy interpretation of the plane wave solutions will be. Now in order to clean the room, in order to start quantizing, it's useful to write down very explicitly what the general solution is and include all the degrees of freedom in dimensionless coefficients, these A that depends on the wave number and the polarization lambda. And so that is the coefficient of the standard plane wave solution, which is also the plane wave solution of the Klein-Gordon equation. I mean, remember that we interpret the vector potential as solving essentially the Klein-Gordon equation with mass 0. So we find back the same plane waves as we did before. Now they appear in a slightly different fashion in the general solution, because we also have to make sure that the Coulomb condition is satisfied. So that's why we got these non-trivial polarizations, epsilon, so there are two of them, epsilon 1 and epsilon 2, so we're summing over both. And we also put in these normalization factors to make these coefficients dimensionless. And there is the complex conjugate part because, well, we want the vector potential to be a real quantity. So were there any questions about this material that we discussed last week? If not, then, well, what is the obvious thing to do here? Well, to figure out what the energy is in terms of these coefficients A. So we have an explicit expression for the energy H as function of the vector potential. So let's just plug our expansion in there and see what we get. Now, in order to do this, we'll have to, so there are two factors of here. So we have to integrate the position dependence over the volume. So a useful thing for us to do is to slightly rewrite this expansion in terms of components that we know to be orthogonal to each other when integrated. So this is summarized in Appendix E of the lecture notes. So let me write essentially the result of this appendix. So to perform these integrals, we rewrite A in Fourier components that have these polarizations in them. So what do they look like? So they're components, not R, lambda, K, depending only on the position. We take the square root of the volume there, such that that is already normalized out. Then we have these polarization vectors, which depended on the wave number K, and simply the phase depending on R. So as I said, in Appendix E, it is demonstrated that if you take two of these integrated over this volume V, and take one of them, so I take one with wave number K and polarization lambda, and the other one with wave vector K prime and polarization lambda prime, and take the complex conjugate, then these are really orthonormal, meaning that it vanishes unless these wave numbers and the polarizations agree. So that makes it a lot easier to perform this integral. But first we have to rewrite our general expansion, the vector potential, in terms of these polarizations. So let's do that. So certainly this 1 over the square root of the volume, that is already in there. So we only have a 1 over square root epsilon 0 in front, a sum over the wave numbers, sum over the polarizations. We keep this energy dependent factor. And then, well, okay, so the polarization is here, in here, and also the phase corresponding to the position is also here. So the first term is easy. It is simply this Fourier component times the coefficient, ak lambda, and then we only have the the time phase left there. And we said that the second term is simply the complex conjugate of the first term. So let's write that down. Complex conjugate e to the I omega kt. But we would prefer the full position dependence here to be of the form of a single Fourier component in order to perform this integral. So let's try to rewrite the complex conjugate of this Fourier component in terms of its, well, non-conjugate equivalent. Now, what does this complex conjugate do? Well, the only complex factor is the phase. So that is going to change this plus ik dot r to minus ik dot r. So this is nearly the same as taking this Fourier component with k replaced by minus k. Now that would work fine if I could simply take this polarization factor that had to depend on the wave number and ignore the sign in front of the wave number. But we cannot quite do that. So let's remember where this polarization depended on the wave vector. So we have here our wave vector k, so along the direction of propagation. And then these polarizations, they were spanning the plane orthogonal to this propagation direction. Like this, so we had one polarization vector epsilon 1 and another one epsilon 2, okay, depending on k. And we required them to be orthogonal to each other also, and together with the normalized wave vector to form a right-handed orthonormal basis. But now we would like to relate these polarization vectors to the ones that I would get if I take k to go in the opposite direction. Minus k. Now certainly the polarization vectors are still perpendicular to minus k, so they are an orthogonal basis, but it's not right-handed anymore. If it was right-handed to start with, it will be left-handed now. So that means that we have to change at least one of these vectors when we're changing the direction of k. And we can just choose a convention. So the simplest convention is to take epsilon 1 of k to be the same, but we take epsilon 2 of k to then point in the opposite direction. So this would be epsilon 2 minus k. Well, the first one is still pointing in the same direction. So put differently, we can take these polarization vectors to satisfy the following. That if I take minus the wave number, that they're related to the original ones by, if you like, a phase, eta, where eta of 1 is 1, and eta of 2 is -1. Right? That's just a simple abbreviation of switching from this one basis to the other basis. So now it's clear how we can express this part in terms of the original Fourier mode. So this is 1 over square root phi epsilon lambda k e to the minus I k dot r. So this is exactly eta lambda times epsilon lambda minus k. Times u minus k lambda r. So now we can take the Fourier component outside, and we have so why can we take it outside? We still have a minus k here. But, well, I mean, we also have a sum over k. So we could simply split these two sums into 2 and switch your summation variable from k to minus k on the second sum. And then it would be of the same form as the first sum. So we have to switch the k not only here from k to minus k, but also on the coefficient. So we have, let's put r here. This is an a k lambda. Okay, and we also have a, let me give another definition here. Maybe I should not do these things all at once. So for me, ak lambda as function of t is really ak lambda e to the minus omega k t. This is definition. And then for the other one, we get eta lambda times a minus k lambda star of t. Right, so this also takes into account that the sign in front of the omega kt is actually changed from minus to plus. So note also that, well, if we change in k to minus k, luckily omega k does not change under this. Is it clear what I'm doing? So I'm doing several steps at once here. I'm taking the two sums apart, then noticing that I'm summing k. So remember that k really takes values in all integers, C3, except the zero vector. So both signs are included there, so I can simply change the summation variable from k to minus k. So let me just write it here for reference. I'm using reparameterization k to minus k. Yes. Yeah, so I'm putting the time dependence. That's what you mean. I'm putting it in the time dependence of A. So I'm just defining AK lambda time dependence as being AK lambda times this phase factor. So for the first term, it takes these two together, and for the second term, it just takes these two together. This one here, you mean? No, right, exactly. So I've gone here from U minus K lambda to UK lambda. So I'm saying here that what I'm doing is I'm doing a reparameterization from K to minus K. Probably I should have done an additional substep here where I introduce a parameter L equals minus K. So then you get a sum over L with a minus L also appearing here. And then I relabel L again by K to get this summation. And I combine it again with the first part where I did not do a relabeling. Okay, so now we can really perform this integral. And let's do one part at a time. So let's look at the contribution of the electric field. So that's just the time derivative of the vector potential squared. So we get, well, let's write it out. So we have to take the inner product of the vector potential with itself. Now what is convenient is to take the second one complex conjugate. Why? Well, I'm allowed to do so because it's a real field. So the complex conjugates will be the same as whether I do it or not. But since I'm then splitting into things that are not manifestly real, this will be easier to work out. So I get a 1/2 from here. Now the epsilon 0, that clearly cancels both of these square roots of epsilon 0. And then I get a double summation, k and a k prime, lambda and a lambda prime, where the primed versions come from the second factor. I get an h bar over twice the square root of omega k prime. So that's these parts. Then let me write down these terms that are independent of the position. So I have to take a time derivative of them. So I get, for the first one, a dot, so the time derivative, that part. And then a time derivative of the second part, the k prime lambda prime part. And then the only part I've not taken into account is this Fourier component, where all the dependence on the position is. So those parts are still inside of the integral, so I've taken everything out of the integral except for the Fourier components. And it should be clear why I'm doing this, exactly because of the orthogonality relation that I showed before. But here, this part is exactly equal to delta k prime, delta lambda lambda prime. So I get a single summation. You can just forget about the primed versions. Here I get an h bar. Let me take this 2 outside. So I have a 4, and then omega k. And if k prime is equal to k, lambda prime is equal to lambda, then you'll notice that this is exactly the complex conjugate of this. So we get the absolute value of this time derivative squared. Okay, that's already a lot simpler. So let's do the time derivative. So the time dependence of these components, they're simply these phase factors with omega k in there. So that brings down an minus I omega k for the first one, and for the second one, which has a complex conjugate, brings down a plus I omega k. So what do we get? We get an overall factor of omega k squared coming out, so h bar omega k. And because this one brought down a plus I, this one a minus I, get a relative minus sign. Sorry, and a minus k here. And a square. Yes. Yes. Great, thanks. Yeah, so I should have the complex conjugate here and not there. Yes. Yeah, maybe it's because I took this one in red there. Overlooked it. Very good. So I'm not going to do explicitly the magnetic field contribution. So let me just quote the result. So for that, we have to evaluate this integral. So taking the curl of A and the curl of its complex conjugate. And what you get is a very similar expression. With the only difference being that there is a plus sign here. So we can work out what the end result is by adding these up. So we're taking the absolute value squared of a complex number minus a complex number plus the absolute value squared of a complex number plus another complex number. So you can easily convince yourself by just working out this multiplication that the cross terms will actually vanish. They will cancel each other. So we're only left with the absolute values of the first terms and of the second terms. Right, so and two of them, of course. So that turns this 1/4 into 1/2 absolute value k lambda t squared plus, well, okay, I can put a eta lambda here if you like. But okay, eta lambda, that was just plus or minus 1, so I can just drop that factor. I can also drop complex conjugate in the absolute value signs. And for that matter, I can also drop the time dependence, since that is just a phase. So here we really have the absolute value of a k lambda and a minus k lambda squared. Can we further simplify this? Using the same slightly confusing trick that I did before. I mean, is there really a difference between these two terms? Right, I'm summing over k, both over positive and negative integers. So really, these are identical terms. I can just relabel k going to minus k on the second term, and it makes it identical to this one. So really what we end up with is that the Hamiltonian is given by the sum of the absolute value squared of all these coefficients. Right, so okay, oops. Again, using the k going to minus k relabeling. Well, that's quite simple and promising, because the more simple a Hamiltonian is, the easier it will be soon to quantize this. So let's make sure that we understand really what this is representing. And in order to do so, it's more convenient to go to a real parameterization. So here we have absolute value squared of complex numbers, while in classical physics we're more used to working with real numbers. So let's do that. So in terms of the real components, so what are the real components? Well, so the real part of these coefficients, I have to take a plus its complex conjugate, and Okay, let's make it dimensionless. Let's give this a suggestive name. So that is the real part. And the imaginary part, well, how can we get an imaginary part? So we have to take the coefficients minus its complex conjugate. But I can also do this by taking a time derivative, because it differs by sign. So let's take P to be the time derivative of Q. So then I get minus I omega k, aka lambda t, minus its complex conjugate. And let's see what the Hamiltonian looks like in terms of the real and imaginary component. So we still have this sum over the wave number, the sum over the polarization. And if you solve these two equations for A and A conjugate, plug them in there, you get that this is simply square of P plus omega k times the square of Q. Oh, I want this one to be red. Okay, let's do a quick poll. The link is in the chat, or in your copy it from the screen. So each term in this sum is the Hamiltonian for what? Does it look familiar? Let's see. Yes, I think we have a majority vote. Very good. This is the simple harmonic oscillator. Just a simple kinetic term, p squared, and then the quadratic potential term, q squared. So where we think of q as like a position and p as its conjugate momentum. I agree. So I claim that q and p really can be interpreted as position and momenta in the sense that they are canonically conjugate. So what does that mean? How can I check whether two variables in classical mechanics are canonically conjugate? Let's do another poll there. So what should I do? Should I compute the commutator, compute the Poisson bracket, look at the Lagrangian or the Hamilton equations? think back to your, what is it, advanced mechanics course. Okay, let's see what we've answered. No, don't start switching right now. Yeah, so luckily everyone agrees that we should not compute a commutator, and these are classical variables, so they certainly commute. Should we compute a Poisson bracket? Well, this would be a valid answer, except not so useful. I mean, by construction, two variables are canonically conjugate in Hamiltonian mechanics if they have a Poisson bracket that is equal to 1. But, I mean, what is the Poisson bracket? I've not given it to you. Essentially, you would construct a Poisson bracket if you would know that these are canonically conjugate. Then you would say, the Poisson bracket is taking a derivative with respect to Q, and then the other one with respect to P. So that would be a bit circular. Well, an appropriate way would indeed be to go to the Lagrangian. So you have to figure out what is the Lagrangian for the electromagnetic field. Well, that is certainly known, but we have not discussed it. And then indeed, to get the canonical momentum corresponding to Q, you would take the variation with respect to Q dot. So that is certainly a valid answer too. But again, not very useful here because, well, we have not discussed the action principle or the Lagrangian for electromagnetism. So given what we know here, the simplest thing to do is just to check that the Hamilton's equations of Hamiltonian mechanics are satisfied. Because if they are satisfied, then you actually know that momentum is the canonical conjugate of the position. So one of the Hamilton equations, well, essentially just a definition here, that the momentum is given by the time derivative. I'm sorry, let me be a bit more precise there. So what are the Hamilton equations again? Well, it's saying that Q, let me not take this color. It's saying that Q dot K lambda should be equal to the derivative of the Hamiltonian with respect to the momentum. Now, this is of course exactly why we chose this definition of P. So that is not the exact criterion that we have to check. The other Hamilton equation says that the time derivative of the momentum should be minus the derivative of the Hamiltonian with respect to the position. If you know the definition of the momenta, then these would really be the equations of motion for the positions. If I would substitute again the momentum for the derivative of Q. And indeed you can check that this is satisfied. So really this equation of motion gives you back the wave equation. So this implies that these are really canonically conjugate variables. So let me draw the conclusion here, which is now very clear in this formulation of the degrees of freedom, and that is that the electromagnetic field in vacuum, so the free electromagnetic field equation, corresponds to an infinite set of independent simple harmonic oscillators. And to be more precise, we have one for each wave vector. K, and each polarization, each of the two polarizations. Lambda. And these simple harmonic oscillators, they have a frequency omega k that depends on this wave vector. So after the break, we'll cash in on this simple representation by, well, what are we going to do? Quantize the simple harmonic oscillator, something that you have already done in Quantum Mechanics 1, I expect. Are there any questions here? Okay, then I suggest we continue at 4:30. Everyone's back. So as I said, we're gonna now quantize, which should be relatively straightforward since we know that we're dealing with simple harmonic oscillators. So what was the quantum mechanics one way of going to the quantization there? Well, we simply put hats on stuff. So let's do the same here. So we're going to promote these Q's and P's to operators. Well, not just any operators, but operators satisfying exactly the canonical commutation relations, which are the quantum counterpart of the canonical conjugate relations that we just discussed. Canonical commutation relations. So for each wave number, wave vector, and polarization, we'll have one operator, Q, and an operator, P, and they should satisfy that they commute unless they refer to the same mode, and then we should get this IH bar. And of course, the other commutation relations should vanish. But if we know what happens to these Q and P operators, then we also know what happens with the coefficients themselves. So the coefficients A, K, lambda. So let's write down the explicit inversion of these two equations, solving for AK lambda. So that gives me square root of omega k over 2h bar times q. So that is the real part, and then the imaginary part is given in terms of p, where now I have a 2h bar omega k. Let's not put hat just yet there. So these are also promoted to operators. So to what are they promoted in our interpretation of the harmonic oscillator? Let's do a quick poll. So if I put a hat on this A in terms of the hatted versions of Q and P, of course, in order to answer accurately, you should remember whether there is a minus or plus sign in front of the I usually, or you can base yourself on the suggestiveness of this notation, AK lambda. So let's see. Yeah, I think I agree with the majority vote. So this will be the lowering operator. Indeed. If you remember from the old days, this was exactly how you introduce a lowering operator to solve for the eigenfunctions of this Hamiltonian. And they would exactly lower the eigenfunction by an energy h bar omega. So these are promoted to, in this case, a lowering operator. And the complex conjugate to the raising operator for the simple harmonic oscillator. Quantum harmonic oscillator. Now, of course, we're going to interpret them slightly differently. The multi-particle perspective, that should be very familiar from the first half of this course, where we did not call these things raising and lowering operators, but really creation and annihilation operators. So you have the creation operator and then annihilation operator. So this is a dagger. Wait a sec. I think this should be a plus. So there was one person who actually answered correctly given my mistake, and that was the raising operator. What I wrote down was indeed the expression for the raising. But if I have a plus there, then it's really the lowering operator. So this one is really given by the one with the minus sign. Sorry, this is the version which has the time dependence. So it's like the Heisenberg operator. But there is also a time independent version of this, a dagger k lambda, with the explicit time dependence there. So what does this operator do? Well, it adds exactly one quantum in the harmonic oscillator corresponding to wave vector k and polarization lambda. And then we have the annihilation operator, ak lambda of t, which is just the complex, the Hermitian conjugate of that one. So there you also have the time-independent version. And the phase is now given by the opposite. And of course, we also have a corresponding number operator, just counting the number of quanta in this mode, this and lambda, which is time independent. And is given in the usual fashion. So are these really the same type of operators that you've seen for the multi-particle quantum mechanics in Fock space? Well, for that we should check whether they satisfy the commutation relations, the bosonic commutation relations that you've seen before. And this we can really check, of course, because we know that Q and P satisfy the canonical commutation relations. So they satisfied indeed the bosonic commutation relations. I forget primes up here as well. And the other ones, of course, vanishing. So these really look like the creation and annihilation operators that you have seen in the first half. So what are they acting on? Well, they have to act on some states, some multi-particle states. In this case, we're dealing with the electromagnetic field, so these should be photons. So they're acting on multi-photon states that are constructed out of some multi-photon vacuum. So these operators act on multi-photon states in the bosonic Fock space. So what did this look like, this Fock space again? Well, we were just counting the number of particles in the different states like this. So in this case, these labels, they really correspond to the different Fourier modes. So these labels, they represent all the different choices of the wave number of the wave vector and polarization lambda. And these were obtained from the vacuum by acting with these creation operators n1 times, and then this normalization to make it a normalized state in this Fock space. So we have to produce a particle in each of these wave vectors and polarizations a number of times corresponding to the state, acting on the vacuum, so the state in which there are no photons. So this is the photon vacuum state. So this will be the arena in which the quantized free electromagnetic field lives. Now we've taken a number of steps, rewriting the field in terms of Q's and P's and in these A's, and they're acting on this abstract Fock space. But we can go back. We can now ask, so our electromagnetic field represented in terms of our vector potential, well, that also has to become an operator. And it will be an operator that is acting on these states, these multi-photon states. So let's just write down explicitly what this field operator looks like. Well, that's relatively straightforward because we had already expressed them in terms of these coefficients A. So we just have to put ats on them. So the electromagnetic field operator, let's say in the Heisenberg picture, so it's an operator that depends on time, and the state is assumed not to depend on time. This is the most convenient picture. In that case, so let me just copy the formula that I had before quickly. So we had Fourier component, and then ak lambda of t plus eta lambda a minus k lambda conjugate t. So in order to turn this into an operator that acts on these multiphoton states, I just put hats here. So this field, it's like a mixture of creating some photon states and destroying some photon states, or the other way around. And this now becomes a dagger in the operator picture. Now what is nice is that by putting hats on these A's, I have really not changed anything in the space and time dependence. I've only put these hats on top of these dimensionless quantities that sit in front of the phase factor. So there is a phase factor in this Fourier component. There is a phase factor just in this t, which is I e to the power minus I omega kt. So this object as an operator itself, it still satisfies our wave equation. So it's, and this you can check yourself. So it still satisfies Maxwell's equations. At least in this particular Coulomb gauge, so meaning that if I apply the D'Alembert to this operator, it will vanish, and also the divergence. This operator vanishes, seen as operators. So thinking back to the first half of this course, have you seen something very much analogous to this? Does anyone remember? Did you see an operator that satisfied an equation that you already knew? Can anyone comment? Is So remember in the first half, you looked at all these one-particle states, and then Johan introduced the multi-particle states, and then the Fock space with these creation and annihilation operators. He looked at one of these annihilation operators, which, I mean, they really live in momentum space, right? They depend on P. But one can also Fourier transform this annihilation operator to something in position space. Does anyone remember what this looked like and what equation this Fourier transform of the this annihilation operator satisfied in the Heisenberg picture? What wave equations do we have in non-relativistic quantum mechanics that can be satisfied? There was only one, right? Yes, the Schrödinger equation. Very good. So let me. So what was this this operator psi r of t? It was really the Fourier transform of this quantity. So here we're not in a finite box, right? So that's why the notation is slightly different. So this was the annihilation operator of a particle with continuous momentum p. That could take any real value. Then to go back to position representation, it was integrated against e to the I p dot r, and that gave this operator psi, which was called the Schrödinger field operator. And it's shown in the lecture notes that this operator, it satisfies the Schrödinger equation. Even though it's not a wave function, it's really an operator. So it satisfies Schrödinger equation. So this was in paragraph 1.5 of the lecture notes. So this is entirely analogous at our current situation. The only difference really is that we have not turned the wave function of one particle quantum mechanics into an operator version, which is a Schrödinger field operator. We have instead started with the Maxwell equations, which is a different wave equation, and turned the solutions to those into the electromagnetic field operator. So really the analogy is that instead of thinking of the Schrödinger equation as quantum mechanics, we think of the Schrödinger equation as a classical equation, and we really quantize the solutions of this equation. This is what we're doing in the electromagnetic case. So we can turn the vector potential into an operator, but similarly we get also operator versions of the electric field in the magnetic field, which in this case it is simply given by the time derivative and the curl. So then any quantities that we understand in terms of the electric and magnetic field, or can express in terms of these, we can also construct operator versions of them and see how they act on this Fock space. Natural things to look at is, of course, just the Hamiltonian itself. So let's call that the total Hamiltonian. Now, we already know what the answer will be because we already saw that the Hamiltonian was just a sum of independent harmonic oscillators with a specified frequency. And we know what the corresponding quantum Hamiltonian for such a harmonic oscillator looks like. But we can also start from the beginning. We can say we know what this Hamiltonian is in terms of the electric and magnetic field. So let's just put hats on everything and some daggers in the appropriate places, because we certainly want this Hamiltonian to be Hermitian. Now in the exercise, you actually work out this to check whether it agrees with these quantum harmonic oscillators. And you will find we really have the sum over the different wave vectors and different polarizations. And then the number of quanta in these harmonic oscillators. And the familiar plus 1/2 for the harmonic oscillator. So the lowest energy state of the harmonic oscillator is 1/2 h bar omega k. And then the raising operators every time add h bar omega k. But we can do more. We can also ask for the total momentum that is stored in this quantized field. So the momentum in the electromagnetic field is given by integrating the cross product of the electric and magnetic field over space. So this is essentially the Poynting vector, which you may remember from electromagnetism. And this is not a calculation I will do, but I'll just show you the answer. If I plug in the our expression for the vector potential in terms of A and A dagger, and it's again expressed in terms of the number operator there. And finally, we can also look at the total spin in the electromagnetic field, or if you like, this is the intrinsic angular momentum contained in there, which is similarly given by now the cross product of the electric field. Sorry, there should be daggers here. Or certain, now I'm confused. Okay, I should check whether we should put a dagger in or not. Here we should have a dagger. Let me check the lecture notes quickly. Yeah, we should have a dagger here as well. And there what we get is So what are these quantities? So we get the direction of the wave vector, and then a number operator which is not in the basis of the polarization, but in a different basis. So why is that? So these are the circularly polarized bases. So remember that if you have your plane wave traveling in this direction, then what do these two polarizations represent? Okay, so we have like these two basis directions. So if I look at the wave that is in one particular polarization, then the electric field, it will just oscillate in that direction. But this is not a solution that has an intrinsic angular momentum. A plane wave in electromagnetism that has angular momentum to it, it is one in which the electromagnetic field has a helical structure. So it means that the electric field, it does something like this. So what really are these operators? Well, they're linear combinations. So they're constructed from the the annihilation and creation operators that are linear combinations of the two polarizations. With a complex phase in between. And then as usual, you get the number operator by taking a dagger A of this type. So really this counts the number of quanta that are, if you like, clockwise polarized around your propagation direction, and the other one counts the number of quanta that are anti-clockwise polarized around this direction, and adding them or subtracting them gives the total angular momentum that is stored in this field. Now this is quite useful because we see that all these quantities are really expressed in terms of these number operators. So that means that they're really like one particle additive quantities. And we can directly read off from this what the correct particle interpretation is of these operators A and A dagger. So let's do this. So AK lambda dagger, it creates a photon. Okay, so let's see, what did we already conclude about these particles? What are photons? Let's do a quick poll. Let's see. We have deduced from the wave equations what these particles are. So this is a multi-answer. Did I allow multiple selections? Maybe I forgot to do this. Maybe it's not really a sensible. Okay, I'll just show the results, and now collectively you have to take all the correct answers. get rid of the spin zero ones. This is not spin zero. Certainly they are not fermions. Very good. We just said that they satisfy the bosonic commutation relations. Okay, let me stop the poll here. We can't see the bottom. So some people have voted for massless, some of you for spin 1, and some of you for bosonic, and that exactly sums up the criteria that I wanted to hear. So they're bosonic because the commutation relations for A are satisfied here. They are massless because the Klein-Gordon equation that the vector potential satisfies has m equal to 0. And they're spin 1 because, I guess this exercise is still to come, because you're checking that the Maxwell equation satisfies the relativistic principle if the vector potential transforms as a contravariant 4 vector. Spin 1 particle with energy. Well, what is the energy? Okay, let's do so it creates a photon with those properties, and it has energy E and momentum P given by. So please read it off from these two equations that we just deduced. So remember, this is the number operator. So for each quantum in this particular state, k lambda, I get an energy like this. And for each quantum, I get a momentum equal to h bar k. Right, so there is no ambiguity here. I mean, we're really counting the number of particles with this particular wave vector and this particular polarization, and each of them contributes the same amount. So the energy is h bar omega k, and momentum h bar k. Whereas the other operator without the dagger, it takes away a quantum there, so it just kills a particle in that state. Annihilates such a photon. Very good. Well, essentially, this is all that there is to it. We have figure out operators. They're acting on a Hilbert space. This is this particular Fock space that you've already constructed in the first half of the course. And we can interpret what happens when I act with these raising and lowering, so these creation and annihilation operators on there. They just add photons and remove photons. Now, this does not yet fully clarify why before we had such problems with negative energies in this probabilistic interpretation, and now it seems like suddenly we're done. So let's briefly, in the last couple of minutes, revisit where this issue of the negative energy came from and why there is just no issue here. And for this, well, we have to revisit our interpretation of this particle-wave duality of quantum mechanics and contrast what happens in the one-particle quantum mechanics and in this quantized field picture, which is sometimes called second quantization. So why is one-particle quantum mechanics called first quantization and a quantized field second quantization? Well, simply because in one-particle quantum mechanics, the quantum mechanics is really in the wave equation. But when we go to the second quantization, we are thinking of this wave equation as being a classical equation, which still needs quantization. But of course, it's a bit of a misnomer because in no way did we use quantum mechanics to get to the Maxwell equation here. But in any case, on both sides, we have a wave equation, but we're just reinterpreting what the solutions to this wave equation are. So in one particle quantum mechanics, the solutions to the wave equation were the wave functions, describing for a single particle what is the probability distribution of this particle being at a particular position. Well, now the solutions, they're not functions in this framework. The solutions are really operators, so quantized field operators that act on the Fock space. Now this already signals that, well, the interpretation of what then the plane wave solutions are is quite different. So a plane wave solution for one particle quantum mechanics that really had to describe just a single particle and therefore have some energy interpretation to it. But this is not the case for the quantized field operators. I mean, they are just one of the components of this big operator. So what is the consequence of this? Well, in one particle quantum mechanics, we had to make this distinction between positive frequency modes and negative frequency modes. So the positive frequency modes, say for the Klein-Gordon equation, they had a good interpretation. So they correspond to these plane waves where in front of the time I have minus I times a positive real number omega k. So these are the positive frequency modes. Then acting with the one particle Hamiltonian on this, it gives you an energy h bar omega k, which is positive, and acting with your momentum operator on it, it gives you the h bar k. So that is fine. Our issue was with looking at the negative frequency modes, which are there definitely for the Klein-Gordon equation. So where now I have, okay, let me cheat a bit here. Since I only have to change some signs, I have a minus sign. And well, the only thing we could do is really interpret this as a negative frequency solution. Negative momentum, well, okay, opposite momentum with respect to the positive frequency modes. And this was really the only thing we could do to get a proper particle wave duality. This is the wave, this is the particle. So, well, we still have waves in the field operator picture because in the expansion of this operator, we had this AK lambda operator, which was accompanied by the same phase as these plane wave solutions in Klein-Gordon. But we've just learned how we should interpret this. this operator. What does it do? Well, by our particle interpretation, this annihilates a photon of energy h bar omega k and momentum h bar k. And it's simply accompanied by a phase in this operator A. And it is accompanied by a phase. Okay, this thing here. So really, this is very similar to the one particle side. If I have a number of particles in this particular state, then if this interacts, say, with your apparatus, your measuring apparatus, what your apparatus does is it annihilates one of these particles, because that's the only way you can interact with the electromagnetic field. And what your apparatus then feels is this phase that comes accompanied with this annihilation. And this is the same as you would see in your one-particle quantum mechanics. You would just see if I interact with a particle, I see this phase. But the real difference comes now when I look at the negative frequency modes. So they come, okay, let me again cheat, sorry. So they come together with the A dagger operator. So, well, we already know what this does. It creates a photon. Well, of course, of the same energy as the photon that was annihilated by AK lambda. See, so so I have here really plus sign the energy. I also have a plus sign here. Yeah, because this operator is supposed to create the same particle that its cousin annihilates. But now this creation of the operator is accompanied by the opposite phase, complex conjugate phase, which has this negative frequency. So here really we see this difference, that in our new quantized field representation, these negative frequency modes still correspond just to positive frequency positive energy particles. And there is really no issue with negative energies anymore, as we already observed before, because the energy of the electromagnetic field is clearly positive in terms of the electric and magnetic fields. Okay, so I think we're in good shape. Later, we'll apply the same philosophy also to the Dirac equation and the Klein-Gordon equation itself. Really interpret them as classical wave equations which still need to be quantized, and seeing that there is no negative energy problem after all. Before that, next week I'll go into some applications, some consequences of the quantization of the electromagnetic field. So we'll have a look at the Casimir effect, absorption of photons by particles, and also the black body spectrum of a photon gas, which nicely wraps up this electromagnetic story. Questions?